Let's do couple of things. Okay, so it should be live. Check this YouTube studio. Yeah, we had one subscriber. Thank you very much. Yeah, because I'm starting the live stream from another software. Okay, so everything we do is available on this website, BioniChaos.com. Go check it out. Provide your feedback. Keep forgetting Perplexity has a good speech to text, but doesn't have text to speech to its responses. Mm, do, do, do. Yeah, we had the brain. If we go EG on the side, we had that 3D brain, which we want to turn into a musical. So we had the TMS. Doesn't fit the screen and you can't rotate it for whatever reason. That's a real, well, hyper realistic model of the brain. It's actually made of many different parts. I was thinking we could be, there should be a way of actually grabbing it. Yeah, this TMS, transcranial magnetic stimulation simulation. Simulation. Yeah, it's just when you do the mouse business, it's just moving the coil, the TMS coil, it's not moving the brain. Yeah, we had another version. Yeah, because right, so we have a seizure zone. So this is using the same brain models. It's actually telling you which parts of the brain. Yeah, so that's how it's loading. There's multiple parts to it. I don't think it's loading all of them actually to make it a bit quicker, to make it a bit more responsive. And in this case, you can select your essentially symptoms, auditory hallucinations and head turning or muscle stiffening and arm jerks, and it will show you which part of the brain is likely to be affected. So this model, we want to use this model again. Hopefully we don't have multiple copies of it everywhere. Hopefully it's just available in one place and then we could be using it multiple times as well. And want to turn it into like a music generation. So we're talking to Perplexity about syncopation, which is not just changing of rhythm. Right. So essentially, one of the things we're considering is taking this model, turning it into a music generation, because, well, guess what? We also have an EEG brainwaves into music. You can fire it up. We had a different version of it that doesn't actually. Originally, we're doing backend, but and this one still has the backend, but we don't need it. So yeah, so if you have brainwaves into music, then you have this 3D brain model. We wanted to map music onto it. Probably have two options. One scientific and one artistic. And you can probably imagine what the difference would be. Yeah, so we have the 3D model. We have the EEG to music that you can go check on my website, scroll through it. There's no play button at the moment. There should be a play button. This was done quite a while ago. Quite a while ago. So we're kind of going to be combining them all somehow. A music generator. So we also had a synthetic music generator. Synthetic music. Yeah, so we're doing neurology, cardio, biomedical imaging, vision, hearing, EMG, so muscle activity, mental health. Where mental health should be probably gone. We're not really doing it. Well, everything is about mental health, including the stream. Then we have simulations and modeling. Yeah, that's the main thing. So we have some games, data analysis, AI, obviously, education, signal processing, blah, blah, blah. So, music. Uh, wait, we have to select all tools. Yeah, we have a bunch of. Yes, we have, for example, this music generator. Does it have a start button? Yes, it does. This is how it sounds like. Yeah, it's very basic, pretty basic. But what we were thinking is, in the same way, we turn brainwaves, pre-recorded brainwaves, actually from humans in this case, into music. In the same way, we could be turning music into brainwaves or activation of the brain. Activation of the brain. So essentially we'll have music playing and the brain will get activated, and there will be a toggle somewhere between artistic and scientific mode. Now the question is, where would it be getting the music from? Is it from a generator, a music generator, or microphone? Microphone will be easier. We will have to start somewhere. So we have code for all of it. That makes things a bit easier. And then we can change the tempo or note duration or whatever. And see what difference it makes when looking at the brain. That's the general idea. Oh, for each one of those you have the randomness. Yeah, so this tempo, when set to 100% randomness, the tempo should be varying. It's not varying at the moment. It's not varying at the moment. Should we start fixing this, or move to the brain? The brain is more exciting. This brain model has about 100 parts to it, parts of the brain. So we could be activating each one like one at a time, two at a time over there. Question is, which model should we be using for this? It should have keyboard shortcuts as well. Yeah, this is called this Destriox Atlas of the brain. It's one of 2 or 3 open source atlases, so you can just like download, use it for whatever you want. think about how exactly will it look like. How would it look like? Yeah, the other thing is that if you want to make it scientifically accurate, it's probably the resolution on the auditory areas of the brain would not be high enough, because it will essentially have the whole, whatever, auditory cortex 1, auditory cortex 2 as one single thing. So would be able to only do one single color, as opposed to a more detailed visualization simulation. Main question is what model to use. I can do NotebookLM for overview, and probably something like that what was already done as well. Let's do a new NotebookLM. Researching websites. Okay, we have a bunch of papers. Yeah, one of the sources could not import, whatever, remove source. The rhythm of perception, neural entrainment, and auditory oscillation. Well, there's a few questions that we would like to include. Or topics. Yeah, I want to include the epilepsy, music generators, There's also auditory hallucinations related to epilepsy. How do you spell hallucinations? There's some errors in the code for the simulation. Alright, so when you give it these new topics, now I have to give it in the search for sources. It found another 10 sources or so. One of them is my video. So that's nice too. Yeah, I don't think it knows. I don't know. Hopefully it's just organically selected it. I didn't mention my website or anything like that. Should we do an audio? Should we do deep dive, brief, critique, or debate? Let's do debate. We had some success with it prior. We'll do an overview as well. We'll do a critical overview as a video. Quiz is a good fun. If you check BioniChaos.com, you have any questions, comments, suggestions, complaints, whatever else, we do want to know. We're happy to pretend as if we care. Obviously, just give it to one of the bots to respond to. Okay, so we're still waiting on the video and audio. We found a bunch of papers. We're obviously not gonna read them. Not gonna do anything silly like that. We'll be doing a video overview, a longer audio, and it's already generated a quiz. So maybe we can go through the quiz. Actually, we can bring another model to read the quiz for us. Let me stop that annoying music. This is our own music generator, by the way. But yes, it obviously needs more work. Yes, so generally we're doing, we have an EEG to music converter. That's a real EEG and real musical notes. We'll be adding a play button to it at some stage. Go check it out. We have a jazz music generator that we made a while back. Again, the user interface. It's all prototype, so yeah. And more interesting, we have this model of 3D model of the brain, which we are planning to do more things with. So one of the things would be mapping music onto it. But yeah, we'll see how we go with that. Let's actually bring Gemini AI Studio, Google. Thanks, Google. This video is sponsored by all the free Google models. We have this live API. We'll share a screen with it. We wanted to. We are live streaming at the moment, so hopefully I'm not saying anything too silly. We want to do this quiz real quick. Can you read out the questions and the answers? Can you read the question and the answers on the screen?
Sure. The question asks, in the Bauer et al. 2014 study, what evidence suggested that beat processing is pre-attentive for metrically simple rhythms? Then the options are A, participants were able to manually tap the beat perfectly while watching a muted film. Musicians showed significantly higher MMR amplitudes than non-musicians for all rhythmic omissions. The mismatch negativity, or MMR, was elicited by sound omissions even when participants were not attending to the stimuli. The P3A response was found to be identical for omissions on and off the beat. Would you like me to elaborate on any of those?
Can you explain the terminology?
I'd be happy to. Which specific terms from the question or options are you curious about? Like pre-attentive, metrically simple rhythms, mismatch negativity, or something else?
All of it.
Okay, let's break it down. Pre-attentive means something your brain processes automatically without you consciously focusing on it. Metrically simple rhythms are basic, predictable patterns, like a march. Mismatch negativity, or MMR, is a brain response that happens when your brain detects an unexpected change in the sequence, like a missing beat. Finally, P3A is another type of brainwave, often related to how your attention shifts when something unexpected happens. Does that make sense?
Okay, so can you repeat the question and the answers, but this time do not use any terminology. Make it clear to anyone.
Got it. The question is trying to find out how the study showed that your brain automatically picks up on basic rhythm patterns, even when you're not paying attention. The possible answers are people were able to tap along perfectly with the beat while watching a silent movie. Musicians' brains reacted strongly to missing sounds compared to non-musicians. Participants' brains still noticed missing sounds, even when they weren't actively listening. The brain's reaction to missing sounds was the same whether the sound was meant to be on the beat or not. Does that make more sense?
Uh, okay, people were able to tap along perfectly a bit while watching a sound movie. That sounds legit. Musicians' brains reacted strongly to missing sounds compared to non-musicians. That sounds legit as well. Study. Well, we haven't read the study. What evidence? Let's see if without. Okay, so what's the correct answer?
Based on how the findings were described and the terminology used, option C is most likely the correct one. The study showed that the brain automatically notices when a sound is missing from a basic rhythm, even when someone isn't paying attention, which is strong evidence for pre-attentive processing. Does that make sense?
Yeah, that's interesting. That was able to answer the question without reading the paper. Let's. Should we continue or do something else? Okay, can you describe the next question again without the terminology? May make it accessible to anyone.
Sure. The next question is asking, according to a specific model of rhythmic prediction, what happens to how reliably your brain keeps track of the basic rhythm when the music has a lot of offbeat, surprising moments? The potential answers are, your brain's reliability stays the same, while the amount of surprise increases linearly. Your brain focuses more on slower, basic parts of the rhythm to keep things steady. The rhythm becomes too confusing with all the violations, so your brain's reliability drops. your brain works harder to maintain reliability, making up for the increased number of prediction errors. Which of those seems clearest?
Yeah. No, I was wrong. Wait. How do you unhide the answer so get the bot to... Well, we can stop the screen sharing. Okay, and what's the answer in your opinion?
Based on the way the model works, it seems like option C is the most accurate. When a rhythm is
Yeah,
really
well,
complex with lots of unexpected beats, it gets hard for your brain to maintain a clear mental map of the rhythm, so its reliability drops. Does that make sense?
right. Well, that was correct, and I got it wrong. Okay, yeah, those questions are based on the papers, so it kind of assumes you read the papers and understood what they say. Okay, we have the debate, the audio debate ready, but should we do like an let's make a general infographic so we have something to look at while we're listening to the debate. Then we also have a video as well, so how long is the...
Welcome to the debate. Have you
22 minutes. 22 minutes debate. Well, I have to download it, I think. So we play it in a different browser.
welcome to the debate. Have you ever
Should we speed it up as well? Not sure. Do I have 22 minutes? Well, the video is not ready yet. So okay, we should have some infographic. Oh, yeah, it's just... is the text correct? Yeah, the text is correct. I can open it full screen properly.
Welcome to the debate. Have you ever found yourself just tapping your foot to a song playing in a coffee shop, completely unaware that you were doing it, and until you looked down?
Oh, absolutely. Or, nodding your head to a beat coming from a passing car. It just happens.
Right. But what is actually happening in your brain in that exact fraction of a second? I mean, usually when we think about human hearing, we imagine this passive microphone.
Yeah, a very mechanical sort of transfer.
Exactly. The ear picks up an acoustic signal, translates it into an electrical impulse, and the brain simply records the event. It feels like a clean, linear, bottom-up transfer of data.
It really does feel that way. We tend to assume it's a straightforward process. Sound waves hit the eardrum, the auditory cortex lights up, and we instantly have this faithful reproduction of the outside world just sitting in our consciousness.
But the moment you step into the world of music, and specifically rhythm and meter, that passive microphone metaphor suddenly feels, well, woefully inadequate.
Oh, entirely.
Because when you really dig into the neurology of a musical groove, you are looking at a landscape that is intensely active. It is constantly anticipating, adjusting, and reacting.
Yeah, the auditory system is essentially the definition of a dynamic reciprocating system. I mean, it is never just sitting still, waiting for the world to happen to it.
Which brings us to the central question we are exploring today, drawn directly from recent neuroscientific literature on auditory processing. Namely, when we perceive a musical beat and experience that undeniable groove, is our brain actively predicting the future based on learned, top-down internal models?
Or, conversely, is our auditory system simply reacting via a hardwired bottom-up sensory reflex?
It's a fascinating divide.
It is. And it's a debate that emerges from a massive wealth of empirical source material. We are looking at uh, electroencephalogram studies, EEG studies, of rhythm processing, theoretical frameworks like the predictive coding of rhythmic incongruity model, and even deep clinical observations.
Right, looking at patients with Parkinson's disease and temporal lobe epilepsy. So today I will be representing the top-down predictive coding perspective. I'll be arguing that rhythm perception is an active, learned inference process where the brain constantly attempts to minimize prediction errors.
And I will be representing the bottom-up pre-attentive perspective. I'll be arguing that foundational beat detection is an innate, automatic physiological reflex driven by neural entrainment. Essentially, it's a biological response, independent of your conscious expectation or, frankly, your musical expertise.
Well, to really lay out the top-down perspective, we have to understand that model you mentioned, the predictive coding of rhythmic incongruity, which researchers call the PCRI model.
Right.
This framework suggests that the brain uses Bayesian inference to interpret rhythms.
Okay, for the sake of our listeners, when you say Bayesian inference, you essentially mean the brain is acting like a subconscious odds maker, right?
That is a great way to put it, actually.
Constantly updating its bets on what's coming next based on what it just heard.
Exactly. It isn't passively listening, it's actively calculating probabilities based on prior experience. Like if you are listening to a standard pop song, your brain establishes a prior expectation that the snare drum will hit on beats 2 and 4.
Sure, the classic backbeat.
Right. And in this model, the meter, that underlying, steady, abstract pulse you tap your foot to, is the brain's internal predictive model. The rhythm, however, which is the actual physical notes played by the drummer, is the sensory input.
So you are separating the invisible grid from the actual sounds filling the room.
Precisely. And when a note lands slightly off that expected beat, which we call syncopation, that creates a controlled prediction error.
Ah, I see.
Think of the brain as an active DJ. The DJ has an internal track playing in their headphones, right? That's the meter. But they are constantly mixing that internal expectation with the external audio track coming from the speakers in the club. The brain is working continuously, in real time, to resolve the uncertainty between its internal model and the external sensory input.
I come at it from a completely different way. The bottom-up perspective posits that beat processing is a pre-attentive sensory function. It simply doesn't require a high-level DJ making calculated Bayesian bets in the cortex.
Okay, so how do you explain the brain's reaction to rhythm then?
To understand this, we look at event-related potential, or ERP studies.
Let's slow down and ground that for a second. So you're literally wiring people up with EEG caps in a soundproof room and looking for specific electrical spikes in their brains while they listen to audio.
That's exactly it. Researchers place dozens of electrodes on a subject's scalp. They play an ongoing sequence of sounds, a steady rhythm. And then, intentionally, an expected sound on a strong beat is completely omitted.
Total silence where a note should be.
Yes. And when that happens, the brain generates a specific, measurable electrical spike called a mismatch negativity, or MMM response.
Right. And the crucial part for your position is the specific state the subject is in when that spike happens, correct?
Yes, exactly. That MMN spike happens regardless of whether the person is paying attention to the music, reading a book, or even watching a silent movie. I mean, their conscious mind is entirely elsewhere.
So it's totally subconscious.
Completely. This tells us the auditory system is not a DJ mixing tracks. It is a tuning fork. It contains modulation rate channels that physically entrain to acoustic frequencies. Just as a piece of metal resonates when struck by a specific frequency, our neural circuits automatically resonate with the temporal envelope of sounds. It's a physiological reflex built into the hardware, not a cognitive calculation.
Well, if we are just biological tuning forks, as you say, then explain to me why a Juilliard-trained percussionist hears music fundamentally differently than someone who has never picked up an instrument.
Do they, though?
They absolutely do. If rhythm perception is a learned predictive model, as I am claiming, then musical experts should process beats fundamentally differently than novices, and the neuroscientific evidence supports this. Under the PCRI framework, studies have shown that when musicians hear isolated syncopations, their brains produce much larger MMM and P3M responses.
Right. Those are the magnetic counterparts of the mismatch signals we just talked about.
Yes, they are essentially the brain's prediction error alarms. Because musicians have spent years cultivating a highly refined, culturally learned metrical model, their internal DJ is incredibly precise.
Okay, I follow the logic.
Therefore, any rhythmic incongruity, even a millisecond deviation, creates a massive precision-weighted prediction error. The alarm rings much louder. The system detects the deviation with absolute confidence, proving that this is a learned, top-down cognitive skill. Non-musicians, who naturally have a looser internal model, just don't generate the same magnitude of error signal.
I'm sorry, but I just don't buy that. Let me tell you why. You are relying on studies that typically use highly sterile, abstract metronomic clicks to test rhythm.
Sterile clicks?
Yes, they play a flat beep 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 and see how the brain reacts. But when we look at the Bauer et al. Study, which used acoustically rich stimuli, that entire expertise argument collapses completely.
I'm naturally skeptical here. Define acoustically rich in this context. How does that change the fundamental way the brain receives the signal?
Well, they used stimuli that actually sounded like real music in a physical space. They built a bass pattern at 100 beats per minute utilizing a standard rock configuration. So you have a loud, low-frequency bass drum on the downbeat. You have a sharper, softer snare drum, and even softer, high-frequency hi-hats for the subdivisions.
So a real drum kit sound.
Exactly. This mimics the acoustic complexity of the natural world. When the researchers occasionally omitted a sound on a strong beat versus a weak beat, they again measured that MMN response. And here is the profound kicker. There was absolutely zero difference in the MMN amplitude or latency between professional musicians and non-musicians.
Wait, you're telling me there's absolutely zero difference between a conservatory expert and a novice when a beat is skipped?
None, because the brain detected the omission on the strong beat pre-attentively, purely based on the raw acoustic variance.
But how does acoustic variance negate expertise?
Think about it physically. A heavy bass drum hits the ear with a massive amount of low-frequency energy, whereas a hi-hat is just a tiny splash of high-end noise. The modulation rate channels in the auditory cortex physically locked onto that intense acoustic energy. The brain is reacting to a physical void in the room. It proves that foundational beat detection is an innate human ability, a reflex built into our biology, not a culturally learned cognitive skill that requires years of conservatory training.
I'm not convinced by that line of reasoning because it treats all rhythm as a simple stress detection reflex. Yes, a booming bass drum will trigger a distinct physical response compared to a soft hi-hat. I concede that physics plays a role in the cochlea.
It's a huge role.
But rhythm in human music is rarely that literal. In fact, often the most profound sense of the beat occurs in the silence, when the beat isn't played, which brings us to the phenomenon of groove.
Ah, groove.
Right. If beat detection is completely innate and automatic, as you suggest, why does the physical urge to move to music, what we call the groove, vary so wildly depending on the rhythm's complexity?
You're referring to the inverted U-shaped relationship that researchers see when they study syncopation.
Exactly. Studies show that if a rhythm is too simple, like a perfectly steady metronome, we feel absolutely no groove. We don't want to dance to a clock ticking.
Fair enough.
Conversely, if a rhythm is too complex, like avant-garde free jazz that is highly syncopated, the groove falls apart completely. We feel lost. We actually feel the most pleasurable urge to move our bodies with moderately syncopated rhythms, James Brown, Motown, classic funk. This is because moderate syncopation offers the perfect sweet spot of prediction errors.
Walk me through the mechanics of that. How exactly does an internal prediction error lead to physical pleasure and the urge to dance?
Through active resolution. According to the top-down model, when we hear a moderately syncopated rhythm, our brain's predictive model is optimally challenged. There is just enough unpredictability to be engaging, but not enough to overwhelm the system.
Okay, so we're engaged, but why the movement?
When we feel that gap, we literally move our bodies. We tap a foot, we nod our head. We do this to provide proprioceptive feedback. Our physical movement feeds sensory data back into the brain to anchor the internal meter and self-suppress those prediction errors.
Huh.
This active uncertainty resolution is intrinsically rewarding, and we know this because it is governed by the basal ganglia, which is a subcortical structure heavily involved in dopamine and reward loops.
So you're saying the body is acting as a physical mechanism to stabilize the brain's internal guesswork. The dancing is the brain paying out a neurochemical reward for solving the puzzle?
Precisely, and we see the ultimate profound proof of this in clinical populations. Look at patients with Parkinson's disease.
Right, the dopamine depletion.
Yes, Parkinson's is tragically characterized by dopaminergic depletion in the basal ganglia. The reward fuel is running low. When tested on groove, Parkinson's patients shift their preference significantly away from moderate syncopation and toward much simpler rhythms.
Because they lack the dopamine to process it?
Exactly. Their depleted reward circuitry simply cannot afford the high computational cost of complex prediction errors, so that inverted U-shape shifts to the left. This proves beyond a shadow of a doubt that groove is an active, neurochemical, top-down reward-seeking behavior. It requires the brain to calculate errors and seek physical resolution using dopamine as currency.
That's a compelling argument. But have you considered the research by Hickok and his colleagues on what they call the rhythm of perception?
I'm familiar, but frame it for us.
You're attributing groove to a high-level drive for epistemic affordance, this grand cognitive quest to resolve uncertainty for a dopamine hit. But what if groove is just a physical manifestation of a raw neural oscillation that simply cannot stop firing?
You're talking about a perceptual echo. But how does that manifest physically?
Well, Hickok's team ran a truly fascinating experiment. They had subjects listen to a 3 Hz amplitude-modulated noise. 3 Hz equates to roughly 180 beats per minute, which is the tempo of a fast walk or the rhythmic envelope of human speech syllables.
Right. It's a very foundational biological pace.
Exactly. Then they suddenly stopped the noise entirely, leaving a period of unmodulated silence. During that silence, they played a random faint 1 kHz tone and simply asked subjects to detect it.
Let me guess. Their ability to hear the tiny tone wasn't constant throughout the silence.
Far from it. The subject's ability to detect the tone continued to oscillate antiphasically for several cycles after the rhythm had completely stopped in the room.
Okay, explain antiphasically for us. What does that actually look like in the data?
Think of a heavy pendulum. If you push a pendulum back and forth at a steady rhythm and then suddenly stop pushing, the pendulum doesn't just freeze in midair. It keeps swinging on its own momentum.
Sure, physics.
That is what's happening in the auditory cortex, when the phantom rhythm in the silence should have been at its peak, meaning the brain's filter was fully entrained to expect a loud noise. The subject's detection of the tiny real tone was at its worst. It was masked by the expectation.
Wow.
Yeah. And when the phantom rhythm was at its trough, detection was best. The brain's sensory threshold was literally swinging back and forth. The auditory system created a perceptual echo in its modulation rate channels.
So you're arguing that the urge to move, the groove, isn't a complex reward-seeking behavior at all, but just us physically writing out a biological wave?
Yes. Our brains operate on nested theta-gamma neural circuits. Imagine the slow theta waves as the long ocean swell, and the fast gamma waves as the tiny ripples on top. Those slow theta waves physically entrain to the slow rhythmic envelope of the music.
Okay, I'm visualizing this well.
When the music features syncopation, spaces where a beat is expected but absent, that physical ocean swell doesn't just stop. It keeps rolling by reflex. The groove you feel might simply be the physical friction of your bottom-up sensory filters oscillating on their own momentum. It's biological inertia. It is not Bayesian inference.
I see why you think that, but let me give you a different perspective. I certainly don't deny that neural oscillations exist. I mean, the EEG data is abundantly clear on that.
It is undeniable.
But to claim that these oscillations are entirely independent of high-level top-down predictive brain states ignores what happens when the external sensory system is bypassed entirely. Let's look at clinical abnormalities, specifically temporal lobe epilepsy, or TLE.
The auditory hallucination data. It's a wild phenomenon, but how does it support a predictive model?
Well, when some patients with TLE experience a seizure, or the aura leading up to one, they suffer an electrical storm in the temporal lobe. The brain is misfiring, generating completely chaotic, random electrical noise.
Pure neurochaos.
Right. But the patient doesn't hear TV static. They hear a massive choir, or a childhood piano melody, or a deeply structured, complex rhythm. Why does random electrical noise produce a symphony? Because the brain's fundamental architecture is a predictive engine. It abhors a vacuum of meaning.
So it invents the meaning.
Yes, it is so desperate to construct predictive auditory models that it actively forces chaotic internal noise into a structured musical framework just to minimize the error of the chaos.
But you have to admit that is a severe pathology. I mean, it's a short circuit of the hardware. I've seen those studies.
When researchers run this translation, they find that our intrinsic neural states deeply resemble structured, predictive musical patterns. The brain doesn't just passively receive music. Its very operating language is musical prediction.
That's an interesting point, though. I would frame it differently. I actually think TLE and EEG to music translations reinforce the bottom-up model.
Really? How so?
Let's start with the EEG translations. If you map a 4 to 8 hertz theta wave to a musical note on a synthesizer, of course it sounds like a rhythm. But that simply proves that the brain naturally operates on raw, measurable, physical frequencies. You are just playing the brain's internal tuning forks out loud. It proves the biological entrainment is there.
But what about the complex hallucinations in TLE? I mean, a tuning fork doesn't invent a Beethoven symphony out of thin air.
True, but those complex hallucinations stem from the limbic structures, the deep brain areas governing emotion and memory, misfiring and bleeding their stored data into the sensory processors.
Which sounds pretty top-down to me.
Not necessarily. The fact that an electrical storm in the temporal lobe triggers a specific, structured sensory experience proves that the architecture for rhythm and pitch is biologically hardwired into those specific regions. It doesn't rely on a high-level cognitive Bayesian guess happening in the moment.
So the hardware just turns on.
Exactly. The hardware is just being activated artificially by the seizure. Think of it this way. If you press the physical play button on a tape deck, the tape plays music. That doesn't mean the tape deck is actively predicting the song. It just means the physical circuitry holding the music is intact and was triggered.
Well, so we arrive at a truly fascinating impasse regarding the fundamental nature of our auditory experience. To summarize my position, I believe the evidence strongly points to rhythm perception as fundamentally an active, predictive mechanism.
And your key evidence there is the groove research.
Predicting it and seeking neurochemical reward by physically interacting with it.
And to summarize my stance, the absolute foundation of rhythm is pre-attentive and bottom-up. The fact that we see identical mismatched negativity responses in expert musicians and pure novices when listening to acoustically rich music proves this isn't just about learned cultural expertise.
Right, the physics of the sound.
Yes. Furthermore, the perceptual echoes showing our sensory thresholds physically swinging like pendulums after a rhythm stops demonstrate a hardwired physiological entrainment. We resonate with sound the exact same way physical objects resonate with acoustic frequencies.
Yet, despite our deeply different frameworks on the how and the why, I think we both emphatically agree on one profound point. Rhythmic acoustic stimuli have a measurable, almost shocking ability to physically hijack human neural architecture.
Oh, absolutely. Whether it's the basal ganglia calculating errors and seeking a dopamine hit, or the temporal lobe's biological tuning forks oscillating on their own inertia, sound physically changes the very state of the brain in real time. Our disagreement lies solely in whether the resulting phenomena are driven primarily by top-down expectations seeking a cognitive reward, or bottom-up acoustic filters oscillating by pure reflex.
And it really highlights the immense value of looking at music and sound through both cognitive and neurobiological lenses. The source material suggests we are standing on the edge of vast, unexplored territory regarding how our brains interact with the acoustic world. There is so much more complexity to uncover than we ever imagined.
And as always, we leave the ultimate conclusion to the listener to weigh the evidence.
Indeed. We started this discussion talking about the passive microphone, but whether our brains are acting like an active DJ, constantly mixing internal models with external reality, or vibrating like an intricately tuned array of biological forks responding to the physical weight of the world, well, one thing is definitively certain. We are far more than just recording devices. The question remains, the next time you find yourself tapping your foot to a beat in a coffee shop, are you actively trying to predict the future, or has the rhythm already caught you?
I didn't quite get, yes, so that was Notebook LM. Notebook LM. Notebook LM. Yeah, so everything we do is eventually available on BioniChaos.com. Go check it out, provide your feedback. What's the play button at the bottom of the page? It should be on the top. Should be on the top. Tempo works. Yeah, that's the other thing. If the note duration randomness is 100%, this should be varying. It's not varying. So we need some prompts for the developer of this, which is us. Yeah, we wanted to map. So what we have an idea of a web application where we map music, or your sound coming through the microphone, or synthetic music like this, map it to the brain, because this brain has about 100 parts, so we can light up each part individually in some sort of way. We can try to make it scientifically accurate as well. Maybe. I don't think there will be enough resolution. Yes, it is like hundreds of parts to this brain, but just the auditory pathways are the resolution for them would be not high enough. But yeah, we'll see how we go. Yeah, so we were listening to a debate made by Notebook LM. Yeah, it's took a bunch of sources, which is nice. Bunch of sources, turn them into resources, into new resources, hopefully not copyrighted or anything. I don't think. Yeah, I have this 7-minute video. The beat, brain, and breakdown. Not sure. Let's listen to it.
Today, we are diving into the absolutely incredible and sometimes kind of weird relationship between music and our brains. We're going to look at how a simple beat can actually organize our minds and how, for some people, it can do the exact opposite. All right, let's get into it. You know the feeling, right? A great song comes on and suddenly your head is nodding, your foot is tapping. It happens almost automatically. But why? What's the deal with a beat that just kind of hijacks our bodies like that? Well, it turns out the answer is literally hardwired deep inside our brains. So, to really understand this, we first need to look at this fundamental link in our neurology, this deep connection between what we hear and our impulse to move. What you're looking at here is actually pretty profound. When you listen to a rhythm, it's not just the hearing parts of your brain that fire up. Research shows that your motor-related areas also activate, even if you're sitting perfectly still. Your brain is basically rehearsing the movement before you even make it, and that's what creates that spontaneous urge to dance. And this right here pinpoints the exact network that's involved. You see these areas, the premotor cortex, the cerebellum, the basal ganglia. These are not your hearing centers. No, these are the parts of your brain that are crucial for planning and coordinating movement. The fact that they light up just from hearing a sound, it confirms we have this built-in auditory motor circuit, pretty much just waiting for a good beat to drop. Okay, so our brain is wired to connect sound and movement. That's clear. But that doesn't really explain why certain rhythms feel so good, right? The answer to that lies in this really fascinating theory about how our brain is basically predicting the future. It's an idea called predictive coding. And you can think of your brain as this super advanced prediction engine. It's not just sitting back and passively taking in information. It's actively building these little models to anticipate what's going to happen next. And music, with all its patterns and structures, is like the perfect playground for this predictive system. Now, to really get this, check out the difference between rhythm and meter. The rhythm is the complex pattern of notes you're actually hearing. Think of a cool drum solo. But the meter, that's the simple, steady 1, 2, 3, 4 that you tap your foot to. The meter is your brain's prediction of where the beat should land. And the real fun starts when the rhythm starts to play with that prediction. So here's where the magic happens. The pleasure we get from music comes from that little dance between what we hear and what our brain expects to hear. If a rhythm is too simple, it's boring. If it's totally chaotic, your brain just gives up. But these moderately syncopated rhythms, they hit the sweet spot. They mess with your expectations just enough to be surprising, and your brain gets this little reward, a little dopamine hit for successfully figuring it out. And that is the feeling of groove. This powerful link between external rhythms and our own internal brain states raises a massive question. If music can sync up with our brains for pleasure, could we actually use it for therapy? Well, a recent study explored exactly that, looking at how personalized music could help regulate brain rhythms for people with epilepsy. So how'd they do it? They use technology like this, the Neurosity Crown. It's an EEG headset that measures the brain's electrical activity, brainwaves. This lets them see in real time exactly how different musical instruments and styles were affecting the neural rhythms of each person. And the process they developed is pretty brilliant. It starts by measuring a person's brainwave response to find which instruments are most calming for them specifically. That personalized data is then used to train an AI, which can then predict the best therapeutic music for new people based on their unique brain activity. It's truly personalized medicine, all driven by data. And this chart from the study shows you exactly why that personalization is so critical. Now, I know it looks complicated, but just focus on the colored bars. They show different brainwave frequencies for 3 different people. For the person on the left, you can see the violin, that's the blue bar, gives a more balanced response. But for the person in the middle, the violin actually causes high activation, while the piano, the red bar, is way more calming. A one-size-fits-all approach wouldn't just be ineffective. It could actually lead to overstimulation, which is the very thing you're trying to avoid. But this brings us to a really stark and fascinating paradox. Because while music can be an amazing tool for regulating the brain, for a small number of people, it can be the very thing that disrupts it. This condition is called musicogenic epilepsy. And yeah, you heard that right. It's a rare type of reflex epilepsy, where seizures aren't random. They are consistently set off by a specific trigger. And in this case, that trigger is music. The very same patterns that can bring order and pleasure can, for these individuals, actually trigger a seizure. So how can music cause a seizure? Well, the theory points to these hyperexcitable neurons in the brain's auditory networks, which you see highlighted here in the temporal lobes. When a very specific sound is heard, and it can be as precise as a single note from one instrument, it triggers this abnormal synchronized storm of electrical activity. And that cascade is what becomes a seizure. Wildly enough, even the emotion a song brings up can play a role. This double-edged sword of music, as both healer and trigger, just goes to show how much we still have to learn about the brain's rhythms. But what if, instead of just analyzing these rhythms on a chart, we could actually listen to them?
This is the incredible idea behind a technique called sonification. It's the process of translating complex data, in this case EEG brainwave data, into sound. So instead of needing a neurologist to read squiggly lines on a chart, this could make seizure activity understandable to pretty much anyone. And you have to hear this incredible quote from a project at Stanford that describes it perfectly. They translated a patient's EEG into a song with two voices, one for each half of the brain. So when the seizure begins, one of those voices just goes haywire. It becomes an unmistakable audio cue. You don't need years of medical training to hear that something has gone wrong. And this just perfectly captures the real-world potential. I mean, this is not just some cool science experiment. For caregivers or for patients themselves, a simple, intuitive audio alert could be an absolute game changer for identifying seizures in real time, making care faster and so much more accessible. And that brings us full circle. From our basic innate desire to move to a beat, to music being both a precise therapy and a specific trigger, it all comes down to the brain's incredibly complex rhythms. The idea of translating those internal rhythms into a language we can all hear opens up a whole new universe of possibilities, not just for epilepsy, but for understanding things like mood, focus, even consciousness itself. So if we can truly start to listen to the brain, what other secrets is it waiting to tell us?
Yeah, it looks like advertisement to Notebook LM. I don't think it needs to be advertised. What's up? What are you talking about? Yeah, so it's missing a voice model. Notebook LM is missing a voice model. I mean, yeah, just until a couple days ago, the audio, you could have had it in interactive mode, but that seemed to be not available anymore, unfortunately. I don't know where it went. Did I reach some sort of quota? I'm not sure. Did we do a mind map? No, the mind map really helps. Really, really helps. It was also really quick generating it. Music, rhythm, and the brain. Better title. Oops. Yeah, when you click on it on the box instead of the arrow, it actually sends it into the chat. And it's looking through your sources. So it's only looking at the sources that are highlighted. Okay, so we have beat and meter processing, pre-attentive detection, predictive coding, the groove experience. Yeah, so it's taking stuff, social interaction, interpersonal synchronization, social bonding, shared metrical models. Why did they come up with like names like that? Sonata AI music therapy. Yeah, obviously. Personalized instrument prediction, neural network analysis, blah, 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 Parkinson's disease. Clinical and therapeutic applications. Rhythmic auditory stimulation, complexity shift in preference, e.g. to music conversion. Yeah, that's what we are doing. Auditory pattern recognition, neurological phenomena, musical hallucinations, which is can be the case in some some types of epilepsy. Can we like simplify the video? Bite size. Let's generate another one. We seem to not have any usage limits. There's only limits on how many notebooks you can have. Uh, let's look at the code while it's generating another video. Yeah, this seizure zone, can we just map it quickly to a microphone? A seizure zone. Oh, this one has JSON files and things. Not sure why. It's more complicated. Oh, cause yeah, it has the. So this is actually where the brain model is saved, but we probably need to save it in a central location so multiple applications can access it as well. Why do I have a feeling? Oh, we can keep it in the same location. How big is it anyway? How big is that? Um, that's only, yeah, 26 megabytes. So that's workable. Guess it would be kind of nice if we, and I don't know where else we are using it. Yeah, we have the semiology examples. Hey, what should we call it? Audio brain, something. Let's call it mic brain because we will connect it to the mic real quick. Now it disappeared for me. Okay, so the JavaScript is within. It's a good template as well. Let's actually see quickly if it's running locally. Okay, we have it locally. We'll be changing this. Okay, so can we change the code? So instead of keep everything as is for now, but we want to map the audio to the brain, whatever color activation. So essentially, we want to be able to turn on the microphone, and when we do, the areas of the brain that light up will directly correlate to the frequency and the amplitude coming through the microphone. Yeah, we have automatic model selection. Don't know how long will it take. Automatic model selection, agent mode. Agent mode. Let's see if it works. I found MicBrain folder. Yes, it's looking at other files in the folder. I don't know why. No, that's okay. That's okay. As long as we'll just let it do its thing. Hopefully it doesn't break things too much. I mean, we have the original thing saved, so should be okay. Wait, where's the audio? There used to be a text to speech. I don't see it. Replacing 34 lines. Verified existing structure. Working. Okay, I'm dating. I've added audio mapping logic. Now I'm checking for any remaining references or syntax issues before finalizing. Okay. Yeah, if you thought an agent cannot do your job, think again. If you're just listening and smiling nervously, well, you know why. How to use start microphone, speak, play audio. Supposedly it finished. Nothing is moving. Do I need to start the mic? 1 2 1 2 1 2. Start microphone. Allow. 1 2 1 2. Testing. Yeah, it's actually pretty cool. I'm not sure. Well, it is nice. It is kind of what we meant. The previous thing still working? No, this shouldn't be working. That's okay. So it's kind of going dark. I like the different colors, whatever they mean. Do I have only 3 areas of the brain currently being activated? The brain model will update in real time if activation call is driven by frequency and amplitude. 1 1 1. That's kind of nice. It's actually working. It's actually working. What do you think of that? 1 1. We could be using this in the streams instead of any other boring one. Shh. 1. Ooh. Shh. Yes, they do. They are frequency dependent. It's kind of nice. We use 20% of chat messages. We don't need the semiology examples anymore, do we? Yeah, we'll clean up the project later on. Okay, can you explain why only, okay, so first of all, I assume there's a reason we have a symmetric brain activation. I mean, it didn't have to be that way, did it? Can we actually activate like all more parts of the brain instead of just the 3 regions? And can we also update the HTML as well? So we just essentially have the canvas and the description at the bottom of the page. But yeah, we want more areas of the brain activated. But yeah, it's nice that it's actually responding to amplitude and frequency as well. But yeah, we need to be explained how it works, educational purpose, technology and data sources, so on and so forth. And also like an explanation how scientifically accurate it is. Right, let's see. Yeah, so it's updating. Yeah, so we have this brain. I can describe, it's hard to describe in words what we are looking at. Yeah, you should be able to see it as well. But yeah, we have this brain model. It's hyper accurate. It has about like 100 different parts. And currently we made it, well, which model? Which model should we thank for this Raptor Mini preview? Well, I think it's a new Microsoft coding model, whatever. Okay, so we have this mic brain, audio-driven brain activation visualization. We start the brain, whatever. Yeah, it's still working as before. It's still mentioning seizure zone. It's still working on the code, by the way. So stay tuned. I don't know which agent is doing the coding, but it's doing great so far. We only have 3 regions of the brain being activated. I like the colors, the different colors. But yeah, this brain model has about 100 different parts to it. See how it goes. Currently, it broke something. I think it broke something. Well, obviously, Yeah, so low frequencies activate the motor and frontal regions, mid frequencies temporal auditory. High frequencies activate occipital and parietal visual spatial regions. Well, which is not scientifically accurate, is it? Yeah, this visualization is intentionally approximate and educational and does not represent real neural activation. Okay. Yeah, the brain atlas we're using is available on brainde.org. I found a few leftover references. Verify. Yeah, we have agent doing the coding. Raptor Mini doing the coding. It should bring back the visualization. It's kind of the main thing. Still working, doing something. Okay, did it break something? You broke something. Sources, console. Some linting error. Are you kidding me? Are you kidding me? Fix. It's the boring stuff, isn't it? There's a human in the loop if you have any questions. Also, if you want to check out everything we do is eventually available on BioniChaos.com. Go check it out. Provide your feedback. Okay, the linting error went away. To start the microphone. Okay, now we still have the four regions. Why is that one looks funny? Yeah, we need ideally more areas of the brain activated. Okay, 1 2 1 2 is different areas. It's fixed. The linting, yeah, intentionally. The simulation is intentionally approximate and educational. It does not represent real neural activity measured from the brain, nor does it infer true EEG source localization from microphone audio. The left, right, and frequency regions mapping are chosen for visual demonstration only and are not medically validated model of brain activation. It does work though. It does work though. We could have more regions. I like how the left and right is different now. But there's only 1 2 3 4 5 6 regions are being activated. How heavy is it on the... It's only 107 megabytes. It's rotating automatically. The model is rotating. We are continuously working on enhancing mic brain. Well, we just literally made it today, whatever. But with plans for more detailed regional information and additional interactive features in the future. Yeah, so currently it's mapping your microphone. It could be potentially mapping music. And while we have the agent, yeah, that was the last change was we used about like 4% of monthly allowance of tokens, whatever. Context window is at 50%. It's 1% system instructions, tool definitions 8%, messages 15%, files 10%, and total results. Yeah, that's interesting. Because if I start a new chat, okay, currently we only have 6 regions of the brain being activated. Can we increase that and update the text description? We want a section of, we want a whole section on how this web application simulation can be improved in the future as well. But yes, we want more. Maybe a slider. Maybe add a slider to choose how many regions are activated. Like from make the slider go from 2 to all regions available. Regions available. Doesn't understand my pronunciation. To all regions available for this brain model. Let's go. One, two, one, two. Yeah, we can play some music into it. I don't know what music are we allowed to play. Probably none. So we have our own synthetic one. Yeah, problem now it's only mapped to the microphone. It's only mapped to the microphone. Okay, I'll find that music generator thing on my phone. We made like a gazillion of web applications so far. Yeah, we have to search music. Search music. Okay, got it. It's called jazz. Okay, let's start the microphone. Still making changes though. Yep, still making changes. So you can select the activated regions, start microphone. Hopefully it didn't break. Didn't break something. Did it break something? Yes, it did. That's a bit annoying. Can't believe I had to make a manual manual change to the code. Okay, so we have six regions. Can go up to 150. Are they? And let's play this. There should be some sort of the activated regions is weird. Suppose it is 150. I don't think they are all being activated. But it is working. I mean, it's doing the job. We should add the canvas in full screen option. There's also some sort of filter on the microphone. Let me turn it on for a sec. Not sure if it makes any difference or not. I don't think so. $181 megabytes in the browser. That should be fine. Okay, let's read that out loud for a sec. It's the response from the agent.
Checking the available brain model list and current file structure so the slider and activation logic can be integrated cleanly. Searched for files matching /brain_parts.json. 3 matches. Read. Lines 1 to 420. Read. Reviewing the rest of the script in the page footer so the new slider and text section integrate smoothly. Read. Lines 420 to 544. Found all relevant sections. Now applying the UI slider, dynamic region selection, and updated content in one pass. Replacing 62 lines with 181 lines in. Verifying the new slider logic and dynamic band grouping to catch any edge cases before finishing. Read, lines 40 to 220. Read, lines 220 to 360. Searched for regex classify brain models / region count slider / max, region count slider / value, *** mic brain / index.html, 7 results. Read, lines 480 to 510. Fixing the slider initial set.
There's an auto model selection. Hey, can you explain? So first of all, not all the brain regions are being activated, even when I select the whole 150 on the slider. Not all of the brain regions are activated when the sound is going through. So maybe you can explain why, or if you can just like fix the code straight away. Also, can you explain, can you update and explain in detail the part in the text that talks about how the mapping is happening exactly? and the difference between volume and frequency. We will see if that works. But yeah, currently, I don't know if there's more than 150 regions or not. I didn't actually read its response. I mean, its response is highly technical. We really should be just reading the text. Below the canvas should be explaining us what's going on. One, two, 1, 2. Okay. So now it's 6 regions. Now it's 150. Okay, and it's actually fixed it. There's still a hole there. Yeah, one of them is not being activated. I don't know why. When you turn the filters off, yeah, you can actually hear the... Yeah, so you can see the brain getting activated, which is nice. Still some holes on it. Some of the... If you can do control. Can't zoom in. Oh. One. It's kind of nice. It's like what's called like a music visualization of your brain. Okay, it made another change. I don't know what was changed. There's 6 regions, 150 regions. It's actually whatever regions are not currently being activated by the sound. Yeah, so the grayed out. Hopefully it's explained. Now, what is it doing?
Lines in. Replacing 7 lines with 7 lines in. Explanation and fixes.
Wait,
Why not all
that's not
regions were activating?
One,
The
two.
original code had a bug in
One,
the update audio highlights
Had a bug.
function.
What?
When you selected
What
more
bug?
than the regions already classified into the 3 frequency bands, low,
What happened?
mid, high, it would add extra regions from the unassigned list. Regions
No,
that
it's-
didn't match the keyword filters for any band. However, it only colored the regions from the 3 main bands. It didn't apply any color to the added unassigned regions. That's why even at 150 regions, some parts of the brain stayed white. The fix. I
Okay.
updated the code to color every selected region individually. Regions in the low band get
every
orange-red based on low-frequency energy. Mid-band gets yellow based on mid-frequency
Okay.
energy. High band gets blue based on high-frequency energy. 4 unassigned regions, added when the slider goes high, they get assigned to whichever band currently has the highest energy level, so they still light up dynamically. Now, with the slider at maximum, all 150 regions should activate and change color based on the audio. Updated text explanation. I revised the how it works and scientific accuracy sections to explain the mapping in more detail.
Yep.
Frequency determines which regions light up, e.g., low pitches motor/frontal areas. Volume, amplitude, determines how bright the colors are. The louder the sound in a frequency band, the more intense the activation. The text now specifies the exact frequency ranges, 50 to 250 Hz for low, etc., and clarifies that the mappings are simplified analogies for education, not real neuroscience. The slider's role in distributing regions across bands is also explained. Made changes.
Made changes. We like the made changes. And that was Grok code fast. Thank you, Grok. Thank you, Elon. I'm not sure. Yeah, we'll try to improve it some more. Let me know if you have any ideas. So far, so good. I'll make it, everything we do is eventually available on BioniChaos.com. Go check it out, provide your feedback. Should we bring back the audio? Just bring back the audio. Just have to turn the filter off for the music to go through. So this is a synthetic music generator, which is also available on the website. Just using it off the phone, so it goes, because currently this it's called mic brain because it's currently only using your microphone. So it kind of works. Yeah, don't quite understand the mapping. The mapping is a bit odd. Yeah, let's think about it. How do we improve the mapping? Because currently, yeah, there's 3 frequencies: low, medium, high. Amplitude is the intensity of the color, so it's kind of nice. It's probably taking too much. Too much is given to the red frequencies, whatever they are. Yeah, but there is an explanation of how the mapping works. This was another like 4%. The last prompt was like 4% of monthly chat messages quota. We haven't used the inline stuff. Should we use the inline? Currently the inline sits at 0.2%. Update audio highlights. Okay. How long is the code anyway? 670 lines of code. Yeah, the text is fine. The HTML is fine. We have the CSS. The styling is within the same thing. So now we just look at the JavaScript. Function. Okay, script. Function throttle. Classify brain models. Okay. Right, because it's yeah, taking the names. The names. Well, anyway, it works. We could fix. I think too much is going towards too much. So why don't we just select the script? Just the JavaScript. It's long. 600 lines. We can do inline. How do we do that? There's a zooming, min max zooming functionality, whatever. Can we remove it? Don't really need it, do we? Adjust rotation speed. Okay, that works. 1 1 1 1 1 1 1 1 1 1 1 1. Yeah, that's rotating too fast, obviously. Can do it even slower. Yeah, that's better. Don't like it rotating too fast. Display user-friendly error message. Yep. What else? Load all available brain. Parts. That's okay. Color each selected region based on its band. Yeah, those colors, the colors are fine, but the band selection. Classifying brain models. Low, mid, high. Can we add like mid, low? Const mid, low keywords. And then this will be high, low. I'm not sure if that will work. Can try. No, so you have low, medium, high. Can do the annotation for this. Classify brain models into low, mid, high frequency bands based on their names using regex patterns. Yeah, that one is a bit that could use. Okay, so we have low, high, very high. Where is it taking those names? This parietal. Can we list all the names first? And then add the very low, very high? How do we do that? Yeah, we'll need the model to. Yeah, instead of 3 colors, we want 4 colors. So we have very low, low, medium, high, very high. But yeah, we'll need we will need so automatic, yeah, agent mode, automatic a model selection, that's fine. Let's see if it can do it. Yeah, so instead of 3 levels, instead of 3 colors, we want more colors. It will be 5. Yeah, I was trying to use the inline suggestions. It did help, but I didn't use it. I didn't end up using it. Oh, sorry, the audio is horrible because I forgot to turn on the noise suppression. Yeah, now it should be better. Now it should be better. So I'm not sure now. I was only selecting one part of the code. It says working. It says it's doing something, but I'm not sure. It seemed to be stuck. Anyway, the thing is working. I was just saying we'll probably have too much dedicated to 1212. Ooh. No, it's still making changes. Okay, so it's actually doing it. Classify brain models into brain models. No, it's the regions. Very low, low, mid, high, and very high frequency bands. Okay, so it's actually did that. Keep it. 1212. 12. What's happened? What happened to that one? It meant to be 5 colors instead of just 3. I'm still reading some code. Hopefully. Hey, some of the names I think might be wrong. Okay, let's see. 1212. 1, 2. Okay. It's still making. It's still making. That's interesting. It is working. How many colors are there? Yeah, they're meant to be. Is that purple now? 1212. But yeah, too much is going towards that red. And yeah, using too many tokens. Using up too many tokens. Very low. What are the colors for each? Color. What is it doing? It's still analyzing something. It doesn't tell you what it does. Which is weird. Which is weird. 121212. Oops. 1212. 121212. How many colors are there? Yeah, there's this purple. There's that purple. 1, 2, 3, 4. Not sure. 1, 1. Yeah, that color is too similar to the orange. That red is too similar to the orange. Run bash command in the background. It wants to actually, the agent wants to load its own server on a different port. One. Wait, how many? One. One. Well, kind of works. It's trying to test it. I don't know if it doesn't have a vision. I don't think it has vision. This agent, the brain, but it will probably look at the air outputs. I mean, I'm doing it myself as well, but yes, it's loading fine. There's no errors.
Lines 430 to 450. Read, lines 450 to 470. Read, lines 470 to 490. Replacing 1 lines with 1 lines in. Replacing 6 lines with 8 lines in. Read, lines 490 to 510. Replacing 30 lines with 39 lines in. Replacing 1 lines with 1 lines in. Replacing 8 lines with 10 lines in. Replacing 3 lines with 3 lines in. Replacing 3 lines with 3 lines in. Ran terminal command. Python mhttp.server 8000. Task open basketball simulator failed with exit code 127. The brain models are now classified into 5 frequency bands: very low, low, mid, high, very high, using regex patterns based on region names. The visualization has been updated to handle 5 bands with corresponding frequency ranges, colors, and region mappings. The changes include classification logic. Regex patterns now categorize regions into 5 bands, e.g., very low for medial frontal areas, very high for occipital/visual areas. Audio processing. 5 frequency bands are analyzed: 0 to 50 Hz, 50 to 250 Hz, 250 to 1000 Hz, 1000 to 4000 Hz, 4000 to 8000 Hz. Visualization. Each band has a distinct color: red for very low, orange for low, yellow for mid, blue for high, purple for very high. UI descriptions. Updated text to reflect the 5-band system. The application should now provide more granular brain activation mapping based on audio frequencies. You can test it by running the local server and accessing the Mic Brain page.
Yeah, that's fine. Yeah, so it kind of works. There's like missing beats there, like there's holes in the brain. Holes in the brain, holes in the brain. Yeah, it would be fun playing music to this one. I don't know what's up with the zoom. There's something about the zoom. Zooming functionality with control scroll with constraints on zoom level. Let's make it 1000 for a sec. Right. Okay, and the default is 6. We can, yeah, I don't know what the default setting should be. If you have any ideas, do let me know. Yeah, so yeah, nice. So we have a brain. It's an accurate brain model. It's open source. You can grab it for your own projects. We mapped the activation, the colors, to different frequencies and amplitudes, or coming through the microphone. How good is that? Should play music to this. If music is copyrighted, we can just mute. We can just not send the music to the stream. So I'll mute my microphone that goes to the stream, but I'll just play the music to the thing, and looking at whatever my brain, you could try and determine what song is playing. How about that? Can you do that? Let's choose a song. And yeah, I won't be playing it on the stream for copyright reasons. But yeah, something simple. Play something simple. Again, it actually looks pretty cool. So I'll actually choose a song that I don't think is copyrighted, well, because it's also in a different language. So, but it has a lot of like rhythm to it, and yeah, let's put it full screen. Yeah, Mike Brain, performance for you. First in the kind. Need to remove the filters on the microphone. Okay, you get the drift. Well, let me turn the filter back on so the noise doesn't come through. But yeah, you get the drift. It's also important, like, yeah, it gets saturated. Like if I'm too close to the microphone level, you need some sort of yeah, we probably need another controller for sensitivity. Yeah, and obviously the bot can do all these things. How amazing that this is dead. Yeah, it did pretty much everything we asked for. Thank you very much. Thank you very much. Yeah, we'll eventually make it available on BioniChaos.com for you to play with. And well, currently you can, adjust the sensitivity just by moving your mouth away from the microphone. That should be fine. That should be fine. Yeah, let me know if you have any questions. Everything, this model is open source. Everything we do is open source as well. Just go F12 on BioniChaos.com and yeah, there will be some songs that will be better better. Not sure what's happening with the noise suppression. Noise suppression. Yeah, so don't forget to like, subscribe, unsubscribe. You know what to do. Mainly comments. We are mainly after feedback for the website. So if you have any of those, if you have any feedback, do let us know. Do let us know. Forgot a post. We normally take those live streams. We chopping them up to bits and pieces, and post them separately. And we forgot to do. Some of it is automated. Hopefully, most of it will be automated. Well, if you haven't been automated out of your job, I don't know what you're doing. Well, it's either you will automate yourself or your employer will automate you. Which one do you think is better? Which one do you think is better? Which one? Which one? Which one? Because if it can code stuff like this, it's pretty amazing. It's pretty amazing. My brain coming up. Yeah, we should be next time giving it just templates, so we shouldn't be starting scratch. We used to start from scratch, which is not ideal. Now we just take a template. Take a template. The range of the microphone, you can test the range of your microphone as well. The range is pretty impressive. Pretty impressive. Yeah, I had a bunch of models working with us today. Yeah, you're gonna see a lot of this in future streams and videos. In future streams and videos, you're gonna see a lot of this. Yeah, I don't know how do you not use these models anymore. They have a new deep research model. paid version. Why is it paid? Why can't I try it for free? I don't know. 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 Wait, so this is currently, you'll deploy the site. MicBrain. It would not be on the landing page because we'll need some sort of thumbnail for it. We'll need a thumbnail for it. This 2.5 Pro was doing a good job in terms of writing video descriptions and things, titles. Yeah, and we have prompts for it. Yeah, we have prompts for everything. Let's find the. Yeah, so everything we do is on this site, BioniChaos.com. Go check it out. 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 Check it Yes, we're turning this biomedical imaging into games, into simulation games. Simulation games. Simulation games. We have AI doing most of the work for us. So apologies in advance if you don't like AI. What's kind of your problem, not mine? I cannot not use it. I cannot not use it, if you know what I mean. Can't explain. But yeah, we have to use it. Well, mainly because it's like having whatever hundred of employees working for you, doing your work. So I cannot not use it. Okay, I'll have to finish. Have to finish the stream. And nothing in the chat. Yeah, don't forget to like, subscribe, comment. You know what to do. You know what to do. Do you? Do you? Do you? And we're not paying for any models at the moment. We are looking for a CEO for BioniChaos or Bionic Cloud. Actually have another name. We actually have another name that probably no one knows about. That probably no one knows. Yeah, that video is copy as text. A Gemini 2.5 Pro is doing a pretty decent job. Can it replace? Can you replace you at your work? Failed to generate content. What? Ah, yeah, we exceeded the quota, but let's do 3.1 Pro. 3.1. It's not what that's doesn't work. One sec. Yeah, I'll have to finish up. We have a description. Quick. Copy as text. Yeah, there's a lot of copy pasting with AI. Surely should be able to automate all this. Wait. Copy as text. Yeah, we're on LinkedIn as well. We have a group on LinkedIn if you want to check that out. Yeah, we're doing a lot of ECG, EEG stuff. Hey, we are on Discord. We are on Blue Sky. Twitter. Obviously, I refuse to call it whatever it's called now. It's just a silly name. On Reddit. There's something wrong with the text.